Good morning, students. Welcome to the online classes in physics for standard 12th. Today, the topic that we would discuss is related to the drift velocity of electrons and the origin of resistivity. Imagine there be a conductor. This conductor, students, has a large number of free electrons. And imagine that there is no electric field. Electric field is not applied. That means the ends of the conductor we have not connected to any battery. Okay. For example, imagine this piece of aluminum plate. So it is a piece of conductor just lying like that. We have not connected any battery source. The free electrons in this particular material, they will move here and there. And during their motion, they do collide with the heavy ions. Because of collision of these free electrons, what I told, they will collide during their motion. They collide with heavy ions. And we assume these collisions to be elastic. And because of elastic nature of the collision, what will happen? The electrons rebound with same speed. But their direction is not fixed. But the direction becomes random, we say. What is the meaning of random? If after one collision, as is shown by the blue ink, you can see this electron moves in a straight line, it suffers a collision here, it moves in that direction, then here, then here, then here, then here, there. Nobody can predict that after the next collision where the electron will go. The same is true for all the free electrons. Among the free electrons, consider the ith free electron. Let its speed be Vi. All these free electrons, suppose there are n free electrons, n is the total number of free electrons. These n free electrons will have their velocities in random directions. Some might be towards right, some upwards, some downwards, some making some angle to the right, and so on. Therefore, and their values will be almost same, we say. After every collision, the value of velocity will remain same. And that's why the average of these velocities, the average we will denote by this kind of bracket, that should be how much? 0. Remember, velocity is a vector quantity. Because these velocities are in random directions, like so, when you add all these velocities according to vector addition, because of the random nature of these velocities, direction, the total velocity comes out to be 0. What is this? This is the average. Average, how do we find? We sum the velocities and then we divide by the total number. So summation Vi, where I runs from 1 to n, and divided by n. This is the average velocity, and this becomes how much? 0. To be more correct, we can put here vector sign. Is it clear? So this is the situation in absence of electric field. Okay. Next, let's consider what would happen if the ends of the metal are connected to a battery, or what would happen in presence of some electric field. See, those free electrons, they have charge minus E. Q is equal to minus E because they are electrons. In the presence of this electric field, those free electrons will experience some force given as minus E times E. You know, F is equal to QE. What does this formula indicate? This equation indicates that the force on these electrons will be opposite to the direction of electric field because of this negative sign. Electrons, you remember, they are negatively charged. This is represented in this particular figure, students. In absence of electric field, the blue passage indicated by the solid line shows the path. The electron goes like this, it suffers a collision with a big ion, changes the direction of velocity, then again changes, again changes, again changes, and it reaches after some time, say t, it reaches to some point B. In presence of electric field, this path will get a bit deviated because As shown in the figure, the electric field has been applied towards left. Therefore, the force on the electron will act towards right. So you can see the figure represented by the dashed red line. There, the electron experiences a force towards right. Because of that, the path gets deviated towards right. This may not be the exact path because the path may not be straight line. It may be curved also in presence of electric field. But anyway, it's an approximate diagram. And then ultimately, instead of reaching at point B, due to presence of electric field in left towards left direction, we find there is some drifting in the position of electron towards right direction. Instead of landing at B, the electron lands somewhere B dash. So this is the drift. And the direction of drift is opposite to the direction of applied electric field. Why is there a drift? The drift is because of the force experienced by the electron under the influence of electric field. Now, if this be the force experienced by the electron, this implies the acceleration of an electron will be given as force by mass. So it becomes minus E vector upon m, where m is the mass of the electron. Clear? While making notes, please do write the languages also. Now suppose I'll use two symbols, one is small vi, one capital Vi. I am using same symbols as given in your NCERT textbook. Suppose Vi is the velocity, I should write vector form, velocity of ith electron just after collision. So it collides with some big ion and then moves with velocity, starts moving with velocity Vi. Now between two collisions the path is almost straight. So this capital Vi represents velocity of the same ith electron after time t has elapsed since last collision. Let me now explain what I have written. Suppose this is the collision which we are considering. Just after the collision, the velocity of the electron in this direction is how much? Vi. Here this is the situation at t is equal to 0. Now after some time, before next collision, suppose some time t has elapsed. At this point, the velocity is represented by capital Vi. So it is the velocity after time t has passed since the last collision. And this is the velocity, small vi is the velocity just after collision with a big ion. Now its velocity, this is initial velocity, this is final velocity. So you know they are related using this relation. Vi vector is initial velocity Vi vector plus acceleration of the ith electron times t. So now acceleration of the ith electron we can write as how much? E by m with a negative sign. So this becomes Vi minus E upon m times t. Now we will take the average. So average of capital Vi vector will be average of small Vi vector minus E is constant, m is constant. Electric field also is being applied by us, we take it as constant, average of time. This term will be 0. Now what is this? Vi is the velocity of ith electron just after collision. There are n electrons. Just as we have discussed earlier, average of these velocities, average means we have to add the velocities of all the electrons, but all the electrons, do you think they have velocity in the same direction after a collision? No. Some of them might be towards right, some of them might be upward, some of them might be towards this direction, left. Randomly they are oriented in different directions. Because of random nature of these velocities Vi vectors, their summation will be 0 and therefore their average will also be 0. This average value of Vi, we represent it as Vd, and this is what we call as drift velocity or drift speed. Vd vector will become equal to minus E vector upon m into average of this t. I should have written Ti that becomes tau. Where tau, which is average of Ti, is the average time elapsed between two successive collisions. See, there is some time elapsed between these two collisions, then between these two collisions there will be some time, between these two collisions there will be some time, and so on. The average time between two successive collisions, that we call as tau, and we call it as relaxation time. So this quantity tau, we call it as relaxation time. Is it clear, students? So we have got an important relation, Vd is equal to minus Ee by m multiplied by tau. So this is the expression for drift speed or drift velocity, you can write. So this is drift velocity, its magnitude we will write as a drift speed. Now one remarkable result regarding this drift velocity is that this drift velocity expression which you see small e, small m, tau and E vector, all of them are constants. We say it is independent of time. So drift velocity is independent of time. It is the average velocity with which electrons drift opposite to the direction of electric field. Why opposite? You see there is a negative sign. Okay? Now what is the significance of this is that, see, we know in accelerated motion v is given as u plus at. So velocity depends upon time. The greater the time for which you accelerate a body, the more would be its speed. That is not happening over here. Because whatever speed it tends to gain, it loses some of them due to, we say, collisions. The velocity between two successive collisions, one more difference you should understand. When an electron moves between one point to the other, between two successive collisions, this speed is not drift speed. This speed we call it as thermal speed. Even in absence of electric field, these electrons will move with great speeds. The speeds are quite large, hundreds and thousands of meters per seconds. Thermal speed is very, very large. And this speed which we are talking about, the drift speed, would be zero if electric field is zero. In absence of electric field, the drift speed is zero. Electrons will not drift, and that's why there is no current. If electric field is not zero, this drift speed will not be zero, and in that case, so we say if electric field is not zero, then the drift speed is of the order of few millimeters per second. So understand the difference between the normal thermal speed of electron and drift speed of electron. If you have a conducting wire and you connect it to some battery, then the electrons move through this wire with a speed of drift speed, that is few millimeters per second. Suppose 1 millimeter per second. In 1 second it will travel just 1 millimeter. But when there is no connection with a battery, the free electron is not staying at rest. It moves here and there in zigzag fashion in random directions. The velocity of electron between two collisions there, that we call as thermal velocity or thermal speed. Why thermal speed? Because that speed is chiefly regulated by the temperature. If you have a wire at 0 degrees Celsius, if you have a wire at 50 degrees Celsius, the free electrons in the wire at 50 degrees Celsius will have more thermal energy. We say it will have more thermal speed. Some of these ideas you already had in the chapter of thermodynamics in standard 11th. So clearly understand the difference between thermal speed and drift speed. So drift speed is much less compared to the thermal speed. Now let's proceed further. Now let's consider a cylindrical wire, conducting wire. Its area of cross section is A and its ends are suppose connected to some battery, and hence between its ends there is electric field. So E vector is towards left, so the free electrons will drift towards right as per this relation. Now imagine a particular cross section. This cross sectional area is capital A. The free electrons over here will drift towards right because electric field was towards left with how much speed? Vd. So in time delta t, these free electrons will cover some distance. That distance will be how much? Speed into time. So Vd times delta t. Is it clear? If you wait for time delta t at this particular point, then some charges will cross that particular cross section. How many charges will cross? Those charges which have crossed will lie in this particular volume. Now what is the volume of this cylindrical element? The volume, you know, is equal to area of base into length, this height or length, whatever you say. This area is A into this length is nothing but Vd delta t. In this is the volume of this part. Now suppose I use small n as the symbol for number density of free electrons. That means it is number of free electrons per unit volume. Then how many electrons has crossed this particular cross section in time delta t? That will be how much? Number of electrons per unit volume multiplied by this volume. What is this volume? A times Vd times delta t. So what is this? This is number of free electrons that crosses a given cross section in time delta t. Now what is the charge of one free electron? Charge on one free electron is E minus E. So the magnitude becomes E. So if I write charge that crosses, net charge that crosses a given cross section in time delta t will be this multiplied by E, where E is the charge on one electron. So this is the number of electrons, this is charge on one electron. If you multiply that, you will get a total charge. So this much charge is crossing in time delta t. Therefore, what should be the current? Current is charge per unit time. So this is total charge delta q. So delta q, we put the value N A Vd delta t E upon delta t. This cancels. And this gives you the value of I as I is equal to, we'll rearrange the terms, N E A Vd. Let's again get acquainted with these terms. I is the current through the wire. Small n is the number density of free electrons, that is number of free electrons per unit volume. This is the charge on magnitude of charge on an electron. This is cross sectional area, and this is the drift speed, which is given by this particular formula. If you remember, in the last class I have discussed about current density J. So J vector, its magnitude is how much? Current per unit area. So current per unit area will become how much? This much divided by A. So A will cancel. So it will become NE and Vd. Now if you put the value of Vd, this becomes NE, this is the value of Vd, magnitude. So it becomes EE upon M from that equation times tau. So E and E will become E square. Now in vector form, if you write, this is the magnitude of J vector. If you write in vector form, then we can write J vector is equal to this NE square tau by M multiplied by E vector. Last class we have discussed the current density and electric field, they used to be in same direction, so this will be plus. And we have discussed the vector form of Ohm's law, which states that J vector is equal to sigma times E vector, where sigma is called as conductivity. And these two equations, if you combine, J is equal to sigma times E with this, that will give you the value of sigma, the conductivity, as NE square tau upon M. Number density of electron, charge on electron, relaxation time, and mass of electron. So this is the formula for conductivity. And if you remember, we had discussed about resistivity and conductivity, that they are reciprocal to one another. So resistivity will become 1 by sigma, and therefore rho will become m by Ne square tau. So this is all about the concept of drift speed. This derivation usually comes in exam, so please practice it at least once in your notebooks. Next, let us briefly discuss the limitations of Ohm's law. See, conductors that obey Ohm's law, we call them as ohmic conductors. But there are some limitations or exceptions to this particular category of ohmic conductors. There are some conductors that do not obey Ohm's law. Obeying Ohm's law means what? This is the condition, that V must be proportional to I and the graph between V and I must be a linear graph. Even for good conductors, it is found that at high values of currents, the linear relationship between V and I stops. For example, even for good conductors, initially the graph will be almost straight, but after some time it will show deviation, like so. Second limitation is regarding diodes. Diodes you have not yet studied. You will study probably in this particular class, in the later half of this particular session. So just remember the VI characteristics, that means the graph between V and I in case of diodes is not linear. You can see it is non-linear graph. It is a curve. Not only that, when we change the direction of V, the current does not change accordingly. Here it is in microampere, and here in this, that means in the negative side. In the negative side, when we increase the voltage, that means when you reverse the biasing voltage we make it negative. For example, we reverse the polarity, means this one. Suppose in the circuit you have connected the battery like this, then you take it out and reverse its polarity. That is the meaning of reversing the polarity of the battery. Reversing the polarity of the battery should change only the direction of current. Value should remain same. Here it's not happening that way. Here the current reduces to great extent, it becomes in microampere, and in one of the cases it is in milliampere. That happens in diodes. I can't go in much details right now, but that is one of the limitations of Ohm's law. And these limitations are they are widely used. Diodes, transistors, these gallium arsenides, they have wide applications in electronic circuits. Third limitation for Ohm's law, gallium arsenide, this is one material that exhibits VI graph like this. It is not at all a straight line. And if you see this region, with a decrease in voltage, here you see voltage is decreasing, but current is increasing. That is also happening. So with a decrease in voltage, since current is increasing, we say its resistance is negative. So this region is referred to as a negative resistance region. And this part of the graph, as you can see, it is written non-linear region. Since it is non-linear, it does not obey Ohm's law. So these are some of the limitations for Ohm's law. Resistors, students, they are of different types. Basically, the ones which are used for domestic purposes or in laboratories are of two types. One is wire bound resistors and other one is carbon resistors. The wire bound resistors, they are made up of alloy and they are wrapped, they are long. Whereas these carbon resistors are large value of resistances. They have large values of R and are very small in size. Because they are very small in size, it's very difficult to write the value of their resistances. So to know the value of those resistances, in case of carbon resistors, we use a color coding. For example, this resistor will be very small. I think it will be 1 centimeter in size and very thin also. In that there will be color codes like this. I don't have a silver color, otherwise you could have drawn that. So there will be 4 rings or 3 rings at least. These are the color codes which you will have to remember. These are the colors, corresponding numbers, then multipliers, then tolerance. Now what is the meaning of these terms? I'll explain one by one. Now knowing this figure, knowing the color codes, so this representation is referred to as color code. Knowing the color code, This is the working formula. The first two colors in the ring, that will represent the number. Number means 0, 1, 2, 3, 4 up till 9. You see here it is a red. Red, you see where is red? Red is over here. What number corresponds to red? 2. So the first two colors represent numbers, means for R we'll write 2. Then for second R also we'll write 2. They are the significant digits. The third color is multiplier. So you have to multiply with this multiplier. Third color is which one? In this case, that is also red. For red, the multiplier is how much? 10 to the power 2. So this is the value of resistance if the color code is given like this. And then what about fourth one? These values which are indicated, there might be some error in them. The fourth part, that is tolerance, has the value 5%, 10% and 20% for colors gold, silver and no color respectively. Here what is the color? Silver. What is the tolerance value for silver? 10%. So we will write plus or minus 10%. That means the value of resistance will be this much ohm. It can exceed this or it can lag behind this value by a maximum of 10%. So these numbers 0 to 9, then the corresponding multipliers 10 power 0, that is 1, 10 power 1, 10 power 2 to 10 power 9, and then tolerance values 5, 10 and 20 for gold, silver and no color. Now remembering this might be a Herculean task for you. For that, let me tell you one easy way to remember this. This is what my teacher has told me and till now I have remembered. So you remember this. See the first letters. Let me mark them. So I have a mnemonic over here. So B.B. Roy is the name of a person. B.B. Roy. B.B. Roy. In Great Britain. G for Great, B for Britain. Has VGW, very good wife. You see this one, B, the capital letters, B, B, R, O, Y, then G, then B, then V, then G, then W. It will be easy for you if you remember this sentence to write this sequence. Once you write this sequence, it's very easy to write the value of resistance using the color code. Let's see one more example. See this color code given in the carbon resistor. The first color is yellow, then violet, then brown and then gold. So first two colors I have told they represent the numbers, significant digits. So yellow, you see where is yellow? Over here. So number means 4. For violet, 7. So it becomes 47. Then the third color is the multiplier. Third color is brown. So where is brown? You can see this one. So brown, what is the multiplier? 10 to the power 1. So 47 into 10 to the power 1 is nothing but 10. You can write once at least. This is the value of the resistance and then its tolerance will be plus or minus. Now what is the tolerance value? You have to see gold. Gold, what is the tolerance value? 5%. So plus minus 5%. So that is the answer. So 10 power 1 you can simply write as 10. So 47 into 10, that is 470 ohm plus or minus 5% is the resistance of this particular color code. Is it clear, students? So please write these in your notes and remember the sequence of the colors. Now next I would like to discuss very important topic, temperature dependence of resistivity. First I will discuss the variation for metallic conductors and then I'll switch over to insulators and semiconductors. For metallic conductors, this is a relation, just to remember this, that the resistivity at temperature T is its initial resistivity at temperature T0 multiplied by 1 plus alpha T minus T0. Alpha is a constant, we call it as temperature coefficient of resistivity. If you are given alpha value for say copper and if you are given the temperatures say 50 degrees Celsius and 250 degrees Celsius And if you are given the value of resistivity at 50 degrees Celsius, using this formula you can calculate its resistivity at 200 degrees Celsius or whatsoever temperature is given in the question. Now, what important thing we can note here, that rho T will vary linearly with temperature. So it has a linear variation in rho versus T. Therefore, if you plot the variation of rho with temperature for metals, it should be a straight line, which is actually the case like as shown. But this linear relation gets distorted at very low temperatures. So here one important note, I am marking this. So at low temperature, graph is not linear. At significantly high temperatures, means room temperatures and above, the graph is almost linear, but at extremely low temperatures of the order of say 10 Kelvin, 20 Kelvin, 30 Kelvin, 50 Kelvin, at such low temperatures, we don't find a linear relationship between resistivity and temperature even for good metals. Let's try to now reason out, figure out why there is a linear relationship, why the resistivity increases with temperature. See, the resistivity we have discussed, students, the formula goes like this: m by ne square tau. In the topic drift speed, at last we have arrived at this particular result. What is the effect of temperature on rho can be explained on the basis of this particular formula. See, if temperature is increased, upward arrow means increase, downward arrow means decrease, I will use that particular symbol. So if temperature is increased, this implies thermal energy of free electrons will also increase. What is the meaning of that? Thermal energy will increase means they will start agitating faster. Their kinetic energy will go up. So this implies kinetic energy of free electrons will go up. This implies half mv square is kinetic energy. So the speed of free electrons will go up. If the speed of the free electrons, this is not drift speed, this is the thermal speed. So thermal speed, suppose initially the electrons were moving like so. After raising the temperature, they will start moving faster. If they start moving faster, the time between two successive collisions will reduce because their speed has increased. So they will collide very frequently. So the time between two successive collisions, the average time that we denote by tau, so tau will decrease. So temperature will increase, kinetic energy will increase, speed will increase. If speed increases, collisions will take place more frequently and therefore the relaxation time tau will decrease. If tau decreases, tau is in the denominator, this implies resistivity will increase. And this explains why resistivity for metallic conductors increases with increase in temperature. So you have to plot this graph, you have to explain this reason, you can put in your own words. So this is about metallic conductors. But for semiconductors, just opposite happens. Remember, there is one more factor here, n. What is n? N is the number of free electrons. Number of free electrons in metals is almost independent of temperature, almost independent of temperature. Actually, theoretically, if temperature increases, number of free electrons should also increase, but that increase is significantly small in case of metals. So this factor of n does not play a vital role. The vital role is played by the relaxation time factor. So this is the explanation for increase in resistivity with temperature for metallic conductors. Next, let's see the graph of rho versus T in case of semiconductors. Unusually, not as per our expectation, it follows opposite trend as that of metallic conductors. Here the rho value decreases with increase in temperature. Let's see what is the explanation. So we have seen rho is equal to how much? M upon n E square and tau. So there are two factors, one is n and one is tau. Tau, what we have discussed in case of metals, remains same. In case of semiconductors also, that if temperature is increased, this implies thermal energy, thermal kinetic energy of free electrons will increase. That implies speed, thermal speed of the electrons will increase, and if thermal speed increases, tau should decrease, and if tau decreases, rho should increase. But hold on, we are saying that rho decreases and we have got rho increases. This is true. There is another factor n. So this is regarding temperature. Now what happens to n? N in case of semiconductors, for semiconductors, n is strongly dependent on temperature. N rises sharply. What is n? N is the number density of charge carriers. You will study later on in physics, students, that the charge carriers in case of semiconductors are not only electrons but something else also that we call as holes. So don't bother about them right now. So n is, just to remember, number of charge carriers per unit volume. That increases significantly with increase in temperature. So n rises sharply with rise in temperature. If n will increase, what will happen to rho? Rho will decrease. Now there are two factors, factor A and factor B. Because of increase in temperature, resistivity increases, and because of increase in n, resistivity decreases. Oh, I should change my version. T and n are not the factors, tau and n are the factors. Okay. So when we increase the temperature, I am summarizing this. If temperature is increased, then two things happen. Tau decreases and n increases. Because of decrease in tau, resistivity should increase, and because of increase in n, small n, resistivity should decrease. But this second factor is dominant. What do I mean by that? I mean that the decrease in resistivity due to increase in the concentration of free electrons and holes in case of semiconductors, that predominates the effect of increase in resistivity due to decrease in relaxation time. In case of metals, this n, as I have told, does not increase much. So this tau factor was important there. But here, apart from tau, n also plays its role. So whatever there is decrease, whatever increase should take place in the value of resistivity due to tau factor, more than that, the resistivity decreases due to increase in n. And that explains the net effect is that if this is the dominating factor, what will be net effect? Net effect will be that the resistivity will drop down, decrease if temperature is increased, and hence that graph is followed. So I would suggest you to please go through the text also available with you. So I have discussed metals, I have discussed in semiconductors. Insulators also, they will follow similar trend. Of course the graph will not be so very sharp, but this is true for insulators also. In case of insulators also, the n value, small n, will increase with increase in temperature. And then we are left with alloys. Alloys are also made from metals, so their variation is similar to that of metals, like so. So rho versus T for metals, for alloys like nichrome, manganese, etc., will be like this. This variation is not very large. The rho remains almost practically constant over quite a wide range of temperature, and that's why many of our heating elements are made up of alloys. Clear? So please make the notes of these particular things. These are very, very important. The resistivity versus temperature graphs and their explanations. Please be thorough in that. Students, I will stop here. Next class we will switch over to series and parallel arrangement of resistors and electrical power and energy. So till then, goodbye, take care, read well. Students, you can see some questions given in the assignment. Please pause the video, note the questions and do these assignments in your notebook.